Upamanyu Madhow, que es un profesor de la Universidad de California en Santa Bárbara. Bueno, es un experto en la parte de comunicaciones y procesamientos lineales, ha recibido dos premios y la verdad que es un gusto y un honor tenerlo acá con nosotros.
Gracias, Cecilia. Ahora voy a hablar en inglés.
Habla muy bien castellano.
Mi esposa es de acá y voy con mi apellido, se pronuncia Madhow. Okay? So, okay. I'll tell you a bit about my background and the kind of things I've been engaged in for the, in the past 2 decades in one slide, and then go on to the topics of today's talk. So my background is mainly in sort of signal processing and information and communication theory, and I think being sort of having this theoretical and algorithms background gives you a lot of flexibility as long as you're willing to imagine what you're trying to do with it, sort of a concept system that you're trying to do and identify what the fundamental bottlenecks are. And that's what leads to sort of the research programs we've been working on. So I've been, early in my career, basically I was working a lot on cutting edge sort of wireless stuff, interference suppression and such like, and also how to sustain sort of TCP/IP over wireless, etc. That also got spun out into a company, and so that's sort of one part of it, the wireless part. But they also been very interested in positioning and in various forms. And another interesting thing that just sort of happened by accident was we had some project, and by some weird way we came up with a method of improving GPS performance in urban canyons where things can be really off sometimes, and that sort of my students were really interested in doing a startup, and that spun out into something that Uber deployed. So as you can see, essentially what I'm trying to say is that the signal processing and communication type background, I think I'm evangelizing my students who are really interested. That gives you a way, as long as you're open to something that Uber just deployed. Going where the problems are gives you a way. As you can see, essentially of what I'm trying to say is that problems in a systematic way. So what I'm going to talk about today is sort of our program that I've built up with my hardware colleagues on millimeter wave communication, and then also tell you about sort of a guerrilla kind of project on robust machine learning that we are doing in order to try to see if we can make sense of all this deep learning business as industry keeps running with it, but we want to sort of try to understand it and put a more systematic framework to it. So what the topic of today's talk is really why do I call it infrastructure? Well, part of the infrastructure that we are interested in is just having pervasive communication. You've heard that story many times. But also, the other part of it is with the same communication type infrastructure, you can also have sensing, with or without. I mean, you can have sensing infrastructure by itself, but really you have even more of an opportunity if you can have dual purpose use of the communication infrastructure for sensing, and you can see that there's tons of applications of sensing, right? So that's one part of infrastructure that always needs improving, and the other part, of course, whether you are aware of it or not, and I think most of us are aware of it, we have actually machine learning or so-called AI is pervasively deployed already in your search engines, in your recommendation systems, as well as now in many other places where it perhaps shouldn't be, as well as things that you actually experience when you talk to a voice assistant or a chatbot, right? So two key bottlenecks are robustness and interpretability, and that's sort of what I'm interested in. And as I said, we don't have a big program built up on it because we are just sort of coming at it from the side here. Okay, so let me talk about millimeter wave, and please stop me and interrupt me at any time with questions. So, so the funny thing about millimeter wave, what is it? It's, I guess, wavelengths that are officially between 1 and 10 millimeters, I suppose, and 1 millimeter is what, 300 gigahertz, and 10 millimeters is 30 gigahertz. 30 gigahertz is where some people are trying to deploy 5G millimeter wave systems, about 28 gigahertz. And by the time you reach beyond 100 gigahertz, you start hyping it up and calling it terahertz. That's sort of how you'll see all these terms, right? So the key thing is, I mean, when I don't know, over the last 2 decades, one thing that was always a problem was okay, cellular communication is becoming so popular. We're always fighting for bandwidth, how dealing with interference, etc. And once you go to bands that are much higher than the sub-6 gigahertz bands that people use for current cellular and Wi-Fi, you essentially have unlimited bandwidth. Not quite at the licensed spectrum, but unlicensed, you have huge amounts of bandwidth. And beyond 100 gigahertz, we don't even know how we can have perhaps 10 gigahertz of bandwidth in a band and things like that. And then the regulatory framework is not clear, but the idea is that if you can build something interesting, then hopefully the regulators will be interested in promoting it, right? And what is special about it? Well, these tiny wavelengths that you have mean that your antenna arrays, which typical sort of nominal spacing for antennas is half wavelength. You can have a really tiny array in terms of form factor with huge numbers of elements, right? So basically, at these frequencies, the palm of my hand would fit hundreds of elements, right? So you can have very pencil, sort of very directed beams towards wherever you are trying to communicate. The propagation characteristics are rather unique. If you didn't have directional communication, then omnidirectional communication is really a bad idea. As you go to higher frequencies, your path loss scales as sort of the frequency squared. But for fixed form factors at both ends, you can have much more directivity if you point the antennas right and electronically, hopefully, not fixed antennas, and you can actually win in terms of link budget. So, of course, but you then also have to deal with the fact that objects look bigger at small wavelengths, and so you can be blocked very easily. And so that's sort of the situation in terms of physics. In terms of why people are interested now in it is because there have been huge advances in silicon radio frequency integrated circuits, and now you can have relatively low cost sort of CMOS ICs that go beyond 100 gigahertz in terms of RFIC. And packaging is what we call sort of putting, and I'm not an expert, but my friends are, putting the IC together with the antenna, etc. I mean, making sure the electromagnetics are working out. So packaging costs have also gone down, but it's still a huge challenge. But these things are essentially on the cusp of feasibility, and you have working ICs at 28 and 60 gigahertz, and so there's stuff going on, right? So that's why it has migrated from being more for defense applications, radar and things like that, to essentially heading towards mass market. And so we've had a lot of fun with it. I just wanted to sort of make you aware of how, if you start from pretty much zero, which is what we were doing in 2005, looking at the potential of millimeter wave, and ask what are the potential bottlenecks that might come up, there's a huge number of interesting questions that came up, right? So the first question, well, not necessarily the first question, one of the questions I had pretty much at the beginning is, in order to make the link budget work, you need directional communication. Once you have directional communication, how do you make sure things are flexible in terms of you can't just listen to people transmitting in order to decide whether to send or not. Think protocols like carrier sense multiple access don't work. What are the protocols you would do? You have directional communication. How do you make sure things are flexible because you have directional things? Well, how much does it go down, and how much do we benefit from it? So that was pretty early on. We were asking those questions at the system level before really talking about signal processing. Just what happens at the system level? Indoors, if you're routinely blocked with people moving around, with furniture, how can you have sustainable length? And again, so we did sort of detailed modeling of blockage starting from sort of basic physics stuff, and showed that yes, with enough relays and things like that, things would work out, right? Similarly, one thing I was worried about very early on was the big, very attractive thing about these frequencies is that you have huge amounts of bandwidth. The very attractive thing that has made communication scale is that we utilize so-called Moore's law and use computation to implement key functionalities in the transmitter and receiver, and it requires analog to digital conversion, which does not scale very well as the bandwidths go up. I mean, basically the number of bits of resolution available and the cost and power consumption, all number of bits of resolution goes down, cost and power consumption goes up. So we were looking at, well, if I quantize very drastically, what happens to a communication system that is trying to operate in a mostly digital mode? And we realized that even the fundamental information theory of this was not worked out. So again, interesting problems opened up. How much, if you were millimeter wave, again, you shouldn't be fighting physics with millimeter wave. Things get blocked very easily. So you should have small cells that are deployed with base stations that are deployed opportunistically on rooftops and lampposts. What is the capacity you can get? What are the protocols you can get? So that was again something we did relatively early on. This one, I would be happy to go into more details some other time, but this was something that was very interesting. So one of the things the first things people built in millimeter wave were these arrays where to direct the beam, all you could do is control the phase of individual elements, and then you could send only one information stream in a given direction. So all you had was this so-called RF beamforming. From that RF beamforming, you have to decide where to point the beam at various people. Typically, that's done based on feedback and things like that. And essentially, standard techniques for channel estimation for multiple input, for multi-antenna things were always based on the digital paradigm, that you have access to the digital signals from each antenna element. Once you don't have that, you have to come up with new ideas for efficiently learning the channel to different users, and that led us to, again, to develop both algorithms and fundamentals of compressive estimations, where these guys are sending out pseudo-random beams using pseudo-random phases, getting feedback from various mobiles, and then using that, figuring out where they are. So which is far more efficient than searching along a grid for the mobiles, because the more the number of antennas you have, the more fine-grained your search has to be. So again, this was work that was really led us much further than we wanted to go at the beginning. But as we went along, we found more and more stuff that we hadn't thought of. Again, because of the fundamental problem of RF beamforming, how to make it efficient. This one I'm going to come back to, so I don't know whether how familiar you are. There's this concept called spatial multiplexing, which is used routinely in Wi-Fi now. So basically, the idea is in Wi-Fi systems now, you have maybe access point might have 4 antennas or more, and in a very rich scattering environment like this, these 4 antennas here might talk to 2 antennas in a laptop or something like that, and the two And the different antennas here would see a very different response at the antenna array at the laptop because of rich scattering. And therefore, you can send different data streams from the different transmit antennas, and the receiver will receive them with different enough responses that it can sort them out. So that's called spatial multiplexing, and it requires a rich scattering environment so that even closely spaced transmitters can have very different spatial responses at the receiver. Now, as the wavelength gets smaller, even with by spacing, so imagine transmitter space by this much. As the wavelength gets smaller, this might be 100 wavelengths. And there, you don't even need a rich scattering environment to get spatial multiplexing, because your, even in line of sight environments, these two transmitters will see a different response at the receiver. So that's the concept of line of sight MIMO. And again, so this concept, once people had realized this before, but we basically wanted to really understand what the fundamentals were. If you had this much of an aperture at this end and that much of an aperture at that end, how do things scale? So we did an information theoretic analysis, and working with our hardware colleagues, basically showed this sort of demo of line of sight MIMO at 60 gigahertz. And now actually line of sight MIMO is a very well established concept, and now we are looking at how to scale it in an interesting way. So I'll talk about it later. Imaging also, there's a lot of interesting things that are that can be talked about here. The main interesting, big picture interesting thing is radar has been around forever. It's usually used to sort of find objects that are far, far away. So even a plane will look like a point target when it's far away from your radar, right? When you're now using radar for, trying to use radar for consumer applications, like, trying to monitor an elderly person in their home, or in a car, trying to figure out what the environment is like, you're talking about shorter ranges and objects look bigger. So you need sort of extended target models and different, somewhat different approaches, signal processing approaches. And so that leads to a lot of interesting things as well. Okay, so that's sort of the big picture of what was there until about 5 years ago. We kind of knew a bunch of things. So we knew, for example, that we shouldn't fight physics with millimeter wave. Rain can wipe you out outdoors. Blockage can wipe you out indoor and outdoor. Shouldn't go for too high a range. Channels are sparse. Things get blocked, and you pretty much can predict the channels that you have by doing simple ray tracing, and maybe the line of sight plus one bounce and things like that is good enough to model the channel. Blockage can be gotten around with either reflections or relays. You can come up with interesting ideas for channel estimation and tracking. Line of sight MIMO, again, I'll talk about it. It has really huge potential in terms of both wireless backhaul and in-room, very, very high-speed communication. And new models are needed for sensing, right? That's what we knew. And then essentially, at this point, industry was already into talking about 5G millimeter wave and things like that. So we kind of, in academia, always have to be like, at least sort of 10 years ahead. So that's where we basically were starting looking at pitching a center which was trying to look at beyond 100 gigahertz and seeing what it takes to open up that spectrum from a technological point of view. So and one of the theses, I didn't believe it at first, but my hardware colleague, Mark Rodwell, he said, actually, we can scale this mostly digital paradigm where you basically have, if you have an antenna array receiving things from somewhere, you can down convert it to baseband. You can have individual down converters to baseband and actually have access to all the antennas for your digital signal processing. So exactly like MIMO systems today, but with hundreds of antennas. You can do that, he said. Okay, I said, okay, I'll believe you. Let's pitch this. And so essentially the idea was, okay, the hardware effort was increase the number of RF chains to enable all digital MIMO with hundreds of antennas with silicon, perhaps augmented by some other technologies for going further. And then there's a huge problem with scale from the system design point of view, and really requires very intimate working between hardware and signal processing, right? So that was the idea behind the center, and these are things that my colleague is very good at doing these kind of stick drawings, and these are the kind of pitches that he did for picocells, where you essentially have coverage that is one person might need coverage from 3 or 4 access points deployed opportunistically, and essentially you can have in his vision it was hundreds of antennas and hundreds of users, but more likely if you're deploying it like this, it's probably more like 32, 64 antennas and 5 users at a time, because you want to blanket coverage if you can afford it. Similarly, LOS MIMO, things like that. Basically, that's sort of, those are just pictures from proposal. I'll tell you a bit more about specific things in a minute. And then, of course, the pitch for sensing is that not only is your bandwidth going up, which means your range resolution becomes much better, your delay estimation becomes much better, but also the angular resolution can become much better for a given aperture. Your angular resolution is the wavelength divided by the length of the aperture, so that can give you much better spatial resolution in principle. So again, scaling it is a problem. And then this is the kind of center funded by DARPA and Semiconductor Research Consortium, right? So basically, the idea for this particular, we have a new thing that now that I'm going to maybe just mention, but the idea here was just to do crazy thought experiments that say, okay, what is how far can we push these boundaries, at least from a conceptual standpoint, and then see what the technological bottlenecks are. So massive multi-user MIMO, where you have a base station with hundreds of antennas and many hundreds of mobile users, and it's all digital, the processing, and so how do you scale all that, right? And how do you deal with impairments that are going to happen? The CMOS is not going to give me a hugely linear thing. Phase noise is something that people always worry about. As bandwidths go up, the precision of analog to digital conversion is going to be poor. So those are some of the bottlenecks that are there. That's for the and I'm talking about the bottlenecks from my point of view as a signal processing guy. The bottlenecks of building it is quite something else, and we had to give guidelines on that based on our kind of analysis. Line of sight MIMO, again, we want to be able to, especially if you're doing this lamppost-based deployment of base stations, you are not going to dig optical fiber to every lamppost necessarily, so you want wireless backhaul for these guys too, and if I'm going to go at bandwidths of 5 gigahertz or 10 gigahertz on the access link from base station to mobiles, I need even more bandwidth along the backhaul, because it's integrating stuff from multiple base stations. So, and I want to do it low cost using scale in computation. So can we do all digital processing? Can we deploy them opportunistically, so not carefully lined up, pointing at each other, etc. So that's a big challenge there. And radar is another interesting thing, where there's so much development that's happening in communication. Can you reuse that equipment to really give you much better performance than current radar technology that's there? Texas Instruments has a line of very interesting products that we are also using to experiment with. But can you go well beyond that with the large arrays that people are building for communication? So these are some of the questions we had. And I do want to spend enough time on on the deep learning stuff as well. So I am going to adapt as I go along as to how much time I spent on each thing. Cecilia, what time should I target to wrap up the talk? 12:45?
That's
Okay.
that's
Yeah. Because we started at, I think, 11:45, something like that. Okay. So I'll give you a glimpse of this. So this is a kind of crazy sort of thought experiment that we did, right? That essentially, again, nobody will build it necessarily. This is just used to drive technology. So you might have a 256 element linear array. You might have 100 users there. Let's think of the uplink, the receiver side. Your low noise amplifiers and mixers can be nonlinear. The gains in baseband may be nonlinear. You might only have a few bits of analog to digital converter on I and Q. And then you want to do, say, maybe some linear separation of these guys, perhaps linear minimum mean squared error. 140 gigahertz is where the equipment was being built. The ICs were being built. Maybe 5 gigahertz of spectrum with small constellations, QPSK, so 10 gigabit per second, and 100 up to 100 simultaneous users, right? So basically, how good does the RF have to be? That's the first question we were asked by our RF friends. Phase noise, nonlinearities, etc. ADC is our question. We were worried about it, and then classic multi-user detection in principle works. We have a huge history of that, but scale to a very large number of dimensions is the bottleneck. So we kind of need to think together in terms of hardware and signal processing. So I'll give a little bit of detail about one thing, and then just the big picture insights I can tell you also. So some of the insights were that as you scale up the number of elements, you can deal. I mean, it's perhaps not in hindsight not very surprising, but we have very, very specific analytical guidelines that we can give for specs of the low noise amp, ADC, number of bits, things like that. As you scale up the number of antennas, you can average out the impact of nonlinearities. And so there's a standard thing called bus gang approximation for dealing with nonlinearities, linearizing things. We just took it further and essentially got to very detailed system level guidelines based on that. So that was one part of it. The other part, which was very reassuring, was everybody always used to say, oh, phase noise, millimeter wave phase noise is very high. What we showed with a very, we're saying that, okay, we are going to scale the array. We're going to build a large array by tiling smaller arrays. How do you tile? Each smaller array is controlled by a different RFIC, integrated circuit. You have a common clock that is at a lower frequency that is shared by these guys. At each IC will multiply up your clock to the desired carrier frequency. And where do you have phase noise? You have phase noise at the reference that you're distributing, and you have phase noise that is polluting the stuff at however you're multiplying it up using a PLL or some other technique. You have phase noise there too. And then you have to follow through the phase noise through this architecture and say what happens to it, how does it impact multi-user detection and things like that. And again, the answers were reassuring that as you scale up the number of antennas, things become even better than with a single antenna, and the specs are pretty relaxed. That's what happened, and detailed papers on these. And the final thing that I had very much so, I mean, basically was that okay, my initial research soon after my PhD was on multi-user detection, but I knew it couldn't scale to this stuff. So you have a bunch of users coming in. Each of them is seeing a different spatial response, and you can sort them out by linear separation in principle. But the complexity of that is sort of depending on how clever you are, goes as a square or cube of the dimension. That just doesn't work for dimension of hundreds. But the beautiful part of this millimeter wave channel is that really each user essentially has one dominant path. Why do I say that? Well, it's because imagine you have two paths to a given user. This direct line of sight and a bounce, well, those guys, the bounce will be several nanoseconds away from this guy, and essentially at very large bandwidths, that means many, many symbols. So it's not even worth trying to gather energy from that guy. You might as well focus on the main guy and forget about that, because the delay spread is too high and you don't want it. You can just treat it like interference. So really, whether or not there's a line of sight path, the dominant path is the one you should be focusing on anyway. And for a nice linear array, what you have, I guess I'll talk about it in a little more detail, but I want to give a big picture first. Essentially what you have, if a wave that is coming in from one direction essentially causes a linear phase gradient across the antenna, and basically what you have is a complex exponential in space, is a response to a given user. And so if you take the FFT in space, you're going to basically go from 100 dimensions or whatever it is, 256 dimensions, to a very small number to concentrate the energy of a user. So basically the idea of so-called beam space is take an FFT right after the antenna array, and that's the bottleneck in terms of that's an n log n kind of thing, but it has to be kind of done for it to scale. For this to scale, it's almost inevitable. So you do that, and then your users get concentrated in beam space. So essentially, user one might be just energy might be concentrated here, and you might have a few interfering users coming in there too. So you just take a few bins and do multi-user detection at a very local level. So you can parallelize the task of demodulating users by going to beam space. And once we realized this, we also, other people in the center initiated a way of trying to make FFTs run faster, trying to integrate FFTs with ADCs, etc. So beam space is potentially going to be a very useful concept, that not just for 100 plus gigahertz, but anywhere where you have a large number of antennas and dominant paths. So I'm looking forward to seeing what happens with it further. So I'll say a little bit more about this. This is just what I talked about. A particular user across antennas will have, energy, right? But once you take a Fourier transform, it gets concentrated. And essentially, once you have that, everything can be done locally. Everything that we do for multi-user MIMO systems, whether it's linear detection, whether it's nonlinear cancellation, whether it's downlink sort of pre-coding, all those things can be essentially redone in this context in a more efficient way. My student Mohammed had done a bunch of animations. I'm going to show you what he did just for fun. He threw down a bunch of users. Then this is what things look like in beam space once you take a FFT. You're focusing on a particular user. You look for them, using their training sequence. You figure out the right window to demodulate them, and then you do your schemes. And it works pretty well. I'm not going to go through the details here. There's still many issues to be figured out. I'm not going to go into that, but the main thing is that more antennas actually, in terms of what we need from the hardware, more antennas make things simpler in terms of hardware specs. Putting a bunch of tiles together is not a simple issue, so they're still struggling with it, but at least the specs of the individual ICs are simpler. But the DSP stuff, we have only scratched the surface of what needs to happen to actually make everything work out. So there's a new center on that, so luckily. So that's good. The next thing I want to just flash by you is this line of sight MIMO business, because it's really quite interesting, because here's the deal. So many of you might know about time, bandwidth, product, and things like that, degrees of freedom of a channel. If I'm given a particular amount of bandwidth, I can capture signals with that bandwidth by sampling at a multiple of the bandwidth, and so over a given amount of time, you have time times bandwidth samples, and that's the dimension that you have to work with, number of degrees of freedom you have to do anything. You have something very similar happening, very similar equations that come up in terms of what Slepian had done and what you have here, where if you give me an aperture like this, an aperture like that, the number of degrees of freedom you have is the product of the apertures divided by the distance between the transceivers and the wavelength. So the smaller the wavelength, the more the degrees of freedom you can have. So that's the advantage of going to a higher wavelength. And once you go to 2D, that things get squared. So since the bandwidth also scales with the carrier frequency, typically, you basically get a cubic, potentially a cubic gain in data rates by going to higher frequencies. So line of sight MIMO is a very powerful way to truly utilize the benefits of higher speeds. Okay. We had done this was a demo done in 2010 at UCSB with all these. You can see how messy it is, and a few years back, Ericsson did this link in E-band. I think 1.5 kilometers. Okay, 1.5 kilometers, 4-fold spatial multiplexing. You can see that because they are having to go far, they need the spacing to be large too. Remember the equation that you have this, the aperture size has to be large, right? So aperture size has to be large, but the aperture doesn't have to be completely populated by things, right? Essentially, you need as many transceivers as the number of degrees of freedom you need to realize. And they also had 2 types of horizontal and vertical polarization. So they got 8-fold multiplexing and got to 100 gigabit per second over 1.5 kilometers. Very, very impressive, but very bulky. It's not. I don't even know whether they've sold this thing to anybody. It's really not something that. It's not fun to put these things together. I am more interested in this scenario where I can have a compact, relatively compact thing that we can put on a lamppost and look at these lamppost to lamppost links for wireless backhaul, order of 100 meters, and then fairly reasonable form factors. Remember, form factor is precious here. Fairly reasonable form factors. Once you go to 140 gigahertz, can get you to beyond 100 gigabit per second, right? With 4-fold spatial multiplexing, no polarization needed, right? So, CMOS can do it in terms of doing the link budget, but the DSP, how do you scale the DSP to those kinds of rates is a huge issue. ADC is also a bottleneck, essentially, the analog to digital converter. And the other thing really I'm always obsessed about when I think about these things is to make the deployment easier. So you don't want a precise alignment. You just want to go up there and put up these boxes that talk to each other. Just set themselves up and talk to each other, right? So so the classic thing to do in line of sight MIMO is have as many transceivers as the number of degrees of freedom you have, and when you do that, and you put them at the magical spacing that you need to create the array, the aperture of the right size, and then you can ask, okay, what happens when I severely quantize? And we can do something. We wrote a paper about this, but it's very painful to deal with quantization in this classic array of subarrays kind of architecture. But once you go all digital on that end, then and when you have low cost RFICs, you can have many more of these receive antennas than the number of degrees of freedom, and then things get easier. Okay, so essentially that's I want to actually go over this quickly. I don't want to spend a huge amount of time. Basically, you can essentially, instead of doing this, separating them out and creating a diversity of looks can give you much more resilience to quantization noise, for example, we showed. But let's not worry about that. what I wanted to just mention to you, just to is the deployment issue. So when you are deploying things sort of on the opportunistically, you would have endemic misalignments between the transmitter and receiver. They're not. You might have a transmitter with 4 faces, each capable of forming a link, and the 2 faces that are closest to each other would not be pointing directly at each other, but might be misaligned in various ways, right? Once you have that, you have basically intersymbol interference within a stream that you're sending out. You have interstream interference. You have basically a quite messy situation. But if you put and you can't do the things one does in equalization. In equalization, a very standard thing to do is sample at twice the symbol rate, and then you can actually, things work out. You can have reasonable complexity equalizers that do the trick. Can't do that when you're going at really high bandwidths. And so, so the solution for that really that we propose is to just put in more receive antennas than you need. So spatial oversampling, and then by very careful, this guy data stream might arrive at these different receivers at very different times, meaning just several symbols apart. So you kind of need to say, okay, if I'm trying to demodulate a particular symbol of this guy, I might need sample 1, 2, and 3 from this, and sample 5, 6, and 7 from this, etc. So you basically have to figure out an adaptive window to have an efficient space-time equalizer. So that's sort of the, and you can predict the performance pretty well by doing some sort of counting of essentially any time you're trying to do linear interference suppression, which is what this is doing. Essentially, the number of strong interferers you have has to be smaller than the dimension you're playing in, and that's sort of what kind of decides how many receivers do you have, how much of for each symbol, what is the length of the sort of space-time equalizer, and you can figure that out, and it all works out. But my main message is that there are interesting problems that come out when you really think about the deployment issue, right? So, okay, so basically, initial results are pretty positive, but actually there's a bunch of issues that I haven't talked about that need to be still thought about for this so-called wireless fiber being realized with LOS MIMO, and yeah, I think I'll that's enough in terms of that. Yeah, my time is so I'm going to maybe skip the radar thing because I want to talk about the deep learning thing too. So essentially, I'm just going to show you. So what they do in radar right now, for example, for TI, you have maybe a couple of, let me just give you an example, 2 transmitters, 4 receivers. The transmitters send out orthogonal signals. Typically, they're orthogonalized by taking turns of sending, say, chirp signals, right? And the receivers will put together what they receive so that effectively 2 transmitters for plus 4 receivers looks like 2 times 4, which is 8 antennas in operation, essentially. That's sort of the idea of MIMO radar. Again, I don't want to, I just want to indicate this to you. I'm not trying to explain it right now. And then the problem really is that these transmitters, they have a field of view that they have a range that they have, and you're stuck with it. All the things that we know about large arrays with very small elements that can be very, very flexible in terms of how they point and all that is not there at all in MIMO radar. So you don't have any of the gains of large arrays. And the idea is, can you use these large arrays that are there to make radar better? And the idea here, our idea is that essentially, if you send out the pseudo-random beacons that we used for channel estimation, similar to that, and use the kind of super resolution algorithms that we have, you can actually leverage these antenna arrays that are being built for communication for getting better sensing results. So again, that's all I want to say because I want to spend time on the other thing. So again, very preliminary. The only interesting part that I want to leave you with is that for a large antenna array, each element has a fairly large field of view. So the field of view is large, but because it's a large antenna array, you can have very high angular resolution. And you can have longer range because you're pooling the power from the elements and beamforming potentially to go in a given direction. So you don't have the kind of trade-offs that we have in existing MIMO radar. And then, of course, algorithms have to be developed and verified and things like that. And that's what we are still in the process of doing, actually. That's what. OK. So much for millimeter wave. But the main thing is what I loved about this, and I still love about working in this area, is that, especially because I have the privilege of working with top sort of hardware designers, I do get a sense of what the bottlenecks are, and it sort of forces us to come up with new ideas for the system stuff. But also, they tell me what is possible beyond what I think is possible right now, and that opens up new possibilities for design as well. And there are a few ideas that keep us, that drive this research. You want to scale the number of antennas, you want to scale the bandwidth, you want to use the sparsity of the millimeter wave channel, and really you need a geometric approach because these things are at these frequencies rather than a purely statistical approach. And again, by doing thought experiments, we are able to sort of stay ahead of industry, and industry has generally been quite supportive of that because they don't have the time, they're just working on the here and now, and really it's pretty free in terms of thought experiments. The physics, you can't fight physics, and you can't fight the fundamental limits, but other than that, everything is considered open, right? And okay, so a lot going on, and essentially, you can go to our website to find out more if it's all right to me. And there's a new center that has kicked off this year, led by Columbia, both optical and wireless, but UCSB is playing a big role in it. And hopefully we'll continue this work and more to share in the future. Okay, so that's as far as this goes. Let me pause to see if there's any. Is this just too fast to actually generate questions probably? But if you have any, please.
What about interference management?
That becomes much simpler.
Okay.
Because the beams are so directional.
Okay.
That's the beauty of this, right? So the scaling part just becomes the hard part, but interference management is easier. Yeah. Also, the early work. One of the other things is how do you. There is an issue in terms of the half duplex communication. If they're using directional communication, and I'm talking to receiver 1, and somebody else is also trying to talk to receiver 1, that's an issue, and those can be resolved. You need just a different set of protocols to resolve it, but otherwise, it's pretty good, actually. Okay. So basically, that was signal processing for next generation communication sensing, and now I'm talking about next generation computing, so deep networks. Let me start out with some, these are the people who have been doing the work. These guys have graduated, and she's doing the work still. And okay. Right, so it's pretty impressive what has happened. There was this sort of this quantum leap in 2012, right? AlexNet had a huge reduction. Convolutional neural networks showed their power. And then for the specific thing of ImageNet, which is a benchmark for classification of images, there's an architecture that beat human performance in 2015, right? That's what happened in that time frame, less than 10 years back, right? 2015. And now it's basically deep learning is everywhere, right? Essentially, everybody's using it. So that's pretty impressive. And everybody's using it for commercial purposes. It's not research anymore, right? That's embedded in everything. And so people are making money from it. And so suddenly it went from neural networks, became machine learning and deep learning around this time. And now it's AI. So now that they're not worried about another AI winter or anything like that because they're already making money from it. So that's where we are right now. Okay, so that's very impressive. And keeps going, right? This generative AI is basically when you're generating things, right? So text or images, stable diffusion for images, ChatGPT for text, things like that. Protein folding has been predicted. All sorts of things have happened, right? And this is a story that I got from ChatGPT. I'm also involved in a project on sort of resources for early English literacy. So I was just curious about what ChatGPT would do, and it does interesting things when I give it a prompt. So what is the technical foundation that makes all this happen? So I think that's important to understand. So main thing was, okay, you can implement chain rules to adapt parameters, right? So also, if you have enough parameters, it doesn't matter that you have these complex nonlinear surfaces. Some local minima seem to be pretty interesting. You basically do gradient descent on some cost function, and you outperform model-based approaches in more and more fields, actually, right? And there, the theory is, of course, very sketchy, but they do whatever there is says that, okay, having deeper networks and over-parameterizing actually helps rather than hurts. And it's been supported by this infrastructure, right? There's a huge software infrastructure that's been built up, TensorFlow, PyTorch, things like that, that make it very easy to build, to play around, and associate hardware infrastructure with GPUs and all that, right? So people, what do? They basically try out architectures and cost functions. That's what they do. And this is a tiny thing that was in, and this is basically means, some tiny network from way in the past, and now they have this billions of parameters, right? But all these successes, the actual successes, are always in applications where if you fail, nothing too bad happens. So protein folding, even protein folding, you come up with candidates, then scientists will explore it. Recommendations, okay, it's not exactly the right recommendation, who cares? Nobody will even know whether it's not. So that's all good, but then driven by that, you use it in healthcare, you use it in the legal system, you start dreaming about self-driving cars. Makes no sense, right? There you have no guarantees, and now you're using this system which is built for soft failures, essentially, and using it in places where it really impacts people's lives, right? And I particularly got intrigued because when I saw a talk by Ian Goodfellow, Goodfellow has come up with many, many interesting things, but essentially he came up with this kind of observation that essentially you can completely change the output of the black box that you have, the deep learning black box that you have, by putting in tiny perturbations. So this is amplified, right? Tiny perturbations that are adversarially crafted can turn this pig into a plane, right? And this can be done with text, with audio, with little stickers on stop signs that turn them into speed limit signs. Again, there are all these hype cycles about every technology, and one of the hype cycles is about self-driving cars. And so everybody would start out with adversarial examples are bad because they are going to make cars crash. And then somebody actually came up with these kinds of things too, where they put little, and you can have littler stickers than this that do this thing, right? So of course that machine learning is a very hyperactive field. So okay, attacks, defenses, huge number of papers. How typically we say, okay, I have an attack budget of this much. I can have attack budget that is limited to perturbations that are smaller than this amount in some norm, L infinity norm, L2 norm, L1 norm, whatever. And then I can try to defend against it, and then somebody comes up with it, publishes a defense, and then somebody breaks it in 2 months. That's sort of been going on, right? I haven't counted the number of papers, but huge number of papers. And the state-of-the-art attacks are using exactly the same framework pretty much as what we use for training neural networks. So neural networks are trained by adapting the parameters using backprop, right? Typical state-of-the-art attacks are done by adapting the input to, instead of minimizing the loss function, you maximize the loss function. That, again, it's an oversimplification. There's other attacks that are not quite like that, but that's basically how you attack the neural network. You come up with perturbations of the input based on that will do something bad at the output, right? Okay. At the end of the day, after all sorts of signal processing tricks that people have used and tried to use, quantization, there's lots of things. At the end of the day, the state-of-the-art defense is also the same thing. Basically, as you are training the neural network, you also devise adversarial inputs by taking the current snapshot of the network and trying to find inputs that maximize the loss function and use them to continue training them. So adversarial training is what this is called. So that's the state of the art, right? We tried to do something here for a while, saying, oh, I'm a signal processing guy, I'm a comm guy, I know how to clean up perturbations. I'm going to put a box there that kills perturbations and amplifies signals, and I'm going to be fine. We tried a bunch of different things. It worked up to a point, but it didn't reach the state of the art, and it basically it was just too short-sighted on my part, essentially. That I was just trying to say, okay, neural networks work well, and so I'm just going to fix them by putting a layer at the beginning that will deal with perturbations, right? That's basically what I was thinking of. But really, I realized at a point, okay, nobody understands these things. This vulnerability is just a symptom. It's not the main problem, right? The problem is whatever you do, you're getting a black box, whether it's adversarial training or standard training. And so by its very definition, you don't control what features are being extracted at intermediate layers. So how are you going to ever guarantee anything? Never, right? And how are you going to interpret anything? So that's what we are trying to see. Okay, can we actually shape these guys for now, just robustness, and perhaps later interpretability, but let's talk about robustness. And again, we have benchmarks. Our vision system doesn't care about these particular adversarial perturbations, just ignores them, right? Can we get some ideas from neuroscience? And of course, we in communication design things that are robust to noise, so can we get some ideas from communication, right? And instead of just having this big picture end-to-end view, we kind of have to get into the nitty-gritty of the signal processing that's happening in this network. That's the thing. So here's the hypothesis. The only reason we can learn is because natural data is not like fully dimensional. It's living in some low dimensional manifold. Otherwise, there's so-called curse of dimensionality that says if your data is truly high dimensional, you need a number of training examples that grows exponentially with the dimension in order to make sure that for every test point you have a training point close enough. That's sort of the curse of dimensionality. So if things are working, it's probably because there's some low dimensional structures in natural data. And we would like to basically utilize this low dimensional manifolds while using the same infrastructure that has been developed, right? And so one idea is that basically instead of a standard neural network has just a bunch of small outputs at the output of a layer, kind of distributed around 0. Instead of that, can we actually have a bunch of large outputs, a small number of large outputs that are hard to perturb, and a large number of low outputs that we can just kill, threshold out, right? Hopefully that will be more resilient, okay? And potentially more interpretable. Let's not think about it. Now, neuroscience often, they know very little about the brain, truly speaking, but the hypothesis they have is that, yeah, we do have a lot of sparsity, we do have a lot of drastic nonlinearities, and of course, in communication, we're always trying to match to the signals that we're expecting, right? Those are two high-level things you can take away from neuroscience and comm theory, right? And so the big picture is, can we supplement this end-to-end framework with a framework which also looks at layer-by-layer activations and says, I'm going to ask you to be sparse and strong. And so, again, comm means if match to every possible signal you can get. There are too many possibilities here, so you can't match to them. It's exponentially many. But can you have a distributed sort of match filter type of idea where a small number of activations are large, and everything else I can kill. So again, there's too much detail perhaps here, but basically the idea is at a given layer, if something is, if an input during training is activating these neurons, let's sort of perturb them in the direction of the input so that they get even reinforced and make the other guys demote the other guys, right? Hebbian learning is fire together, wire together. Anti-Hebbian is go in the other direction. So that's one idea, and that leads to activation histograms that look like that. So the green one is a standard pattern which it looks kind of Gaussian, and so the negative part gets killed by the so-called ReLU, and then the large you have a you have a sort of bipolar kind of bimodal distribution of activations where it's a bunch of large ones and then a small number of large ones and a large number of small ones, essentially. You are introducing competition between neurons, essentially, to get these sparse strong activations. So this is high, this is low. But if the weights are different for the, if this has very large weights compared to this, that makes no sense. So we have more of a geometric picture of each neuron which viewed as a projection instead of just the inner product between the input and the neuron at each layer. So implicit normalization effectively, so you don't need to put constraints of weights. That's another idea. And it has a very nice, once you put that constraint or normalization, the Hebbian update just looks like I'm taking the weight and aligning it a bit more with the input, and anti-Hebbian update is sort of moving it a bit further away. That's sort of what it looks like. And then the last part is, again, this thing was invented. The nonlinearities in neural networks used to be tan hyperbolic or sigmoid. They didn't help with backpropagation much because basically the gradient vanishes too quickly at the as you saturate. So ReLU, rectified linear unit, has been the standard for neural networks and variants thereof, essentially. So when you look at what's happening in a ReLU, I would like to take these small guys and kill them somehow, but I don't know what is small really. And if there's a perturbation that's riding on top of large activation, it'll just go through up in the network. So, and then add up in weird ways and kill me perhaps. So I'm worried about both this and that. And one idea that we borrowed from neuroscience is divisive normalization, where if you do this, where you have a bunch of neurons competing against each other, whether it's in space or across channels, when you basically divide by, say, the sum or the average or something like that, what happens is now you know what small is, because now you have a measure of scale invariance, because again, this can be chosen to make things scale invariant too, but you have a measure of scale invariance so that I can have an actual number. Okay, this is small, I'll threshold it out, and the other part that happens is there is self-normalization that happens. So a large output, large thing here will also be in the numerator, and that kind of causes things to, the effective nonlinearity curve, essentially. And so the perturbations don't ride up quite so easily. That's sort of what happens there. So I said that already. And so we put all these things together, and I will not tell you these details. I'm just going to tell you what happened at the end. I will not even say this. So let me just give you the example. So basically, we looked at baseline, a simple network, baseline standard thing without any adversarial training or anything, and then our thing with this Hebbian anti-Hebbian business. And you do get increases in accuracy relative to noise and adversarial perturbations. This is not directly going at the adversarial perturbation problem yet, because we want general purpose robustness first, and then we'll worry about this adversarial stuff. And it does appear to do that without any augmentation, without any adversarial training. And then when you compare it against a panel of common corruptions, which are noise, weather things, blur, there's data sets for that as well. Overall, our average performance is better than, say, both standard and adversarial trained networks. And our max min performance is also better. Our worst case performance here is 50% for what? Impulse noise, or maybe it says something, okay. And then adversarial training worst case is 18% for contrast. So in some sense, it does look like it's perhaps more general purpose than adversarial training. I am not going to go through that. Yeah. So I'll just basically summarize here because, yeah. So essentially, the thesis is that the current way of doing things can only lead to black boxes. So just performance guarantees are just impossible in high dimensions with black boxes. And so again, this is a potential. It clearly has potential for robustifying things. And sparsity, sparse and strong may be the key, but the more important thing is you have to tap the activations at the layers and perhaps add elements to the cost function, maybe not exactly what we did, to try to shape those outputs. And it might be also a payoff in terms of interpretability. I don't know yet. But there's a lot more work needed. The results are promising, but the training has to be. And again, we already have interesting ideas there that seem to be working. Training is inefficient right now because the heavy and anti-heavy and the way it's implemented requires sorting as part of it. There are all sorts of other shaping that's needed. And of course, once we get this foundation solid, you can apply it to pretty much anything. But because we are trying to use the same infrastructure and just adding to the end-to-end cost function. Okay, so I'm become a signal processing bigot because essentially I can argue that pretty much everything what you do is signal processing, and pretty much everything that you're trying to do in the next generation, you will have to think of it that way. But you do have to keep expanding your toolkit, right? It used to be just least squares, and the compressive sensing came about. Sparsity became an interesting idea. Turbo codes and all that required message passing. Deep learning is one more thing in our toolkit, and really it goes from theory to hardware and software. So I'm pretty happy with being a signal processing person at this point in time. Okay, thank you. Millimeter wave? Mm-hmm.
For mobile communications, is there an impact of the extra power cost of tracking the user?
Yeah, there is.
Or it's viable for mobile, for moving?
Well, so for example, millimeter wave in 5G has not worked, because the kind of protocols and approaches that are put in place for tracking are terrible. They're just sort of exhaustive search. It's just horrible, actually, what they've put in, the first thing. So a lot more, I mean, basically, I think there are many ideas that will work, but moving it to that is going to take time. So yes, it is a challenge. I think in some sense, what I visualize with this stuff is really people sitting around somewhere and getting something, a very high-speed link to their laptops and things like that, or phones. Also walking is fine, but really if you're inside a car, metal body is going to block it. So there are limitations, and somehow people don't want to think about those too much, because in terms of, you're just sort of putting a direction through, you're putting a bunch of engineers in, there is this hype cycle that drives these things. So I think ultimately, I think the backhaul thing is really interesting, and I think the short range stuff, as well as long range, perhaps a high speed train going, you can track it pretty easily, and you can do that. So I think it has to be sensible. Yeah. essentially. Yeah. Mobile, the big thing that I think that is interesting is your body can block things, and you can move like this, and now you don't see that access point anymore. So you do need sort of a blanket coverage and seamless switching and things like that. So that's the next thing. You want basically a cell-free operation. But again, in terms of the investment in deploying things so densely, the carriers have been slow to accept it, and for good reason. So I think, again, these things, they're cycles, and maybe in 10 years, the technology will be cheap enough that they'll be used enough to hit. Somebody will do it, and they'll start putting things on lampposts. So I'm not worried about that at all.
Bueno, muchísimas gracias.
Okay, gracias, Prof.